Hey, welcome back. In this slice of physics, we're going to be working with graphs for a constant acceleration motion. We will be presented with a velocity time graph of such a motion, and we learn how to interpret details of the motion from this graph. Based on our interpretation, we will develop a motion diagram for this object. And finally, we will look at the corresponding acceleration time graph and position time graph for this motion. So here's the velocity versus time graph that's been given to us that we need to interpret. The first thing to note is there are no numbers on the x or y axis. We're going to do this exercise qualitatively and not quantitatively. We're not going to actually find the numbers for acceleration and position. We're just going to get representative graphs and a representative motion that corresponds to this graph. Secondly, you see that all the lines are straight lines. Every segment here has a straight line for velocity, and you'll remember that slope in a velocity time graph is acceleration, and you'll also remember that slope of a straight line does not change, which is what makes this a constant acceleration motion. It's not constant acceleration for the entire motion, but for each time segment that is shown here, the acceleration is constant because we have a straight line, and then it abruptly changes from one value to another at these boundaries of time interval that are marked. So as usual, I'm going to mark these segments of motion in different colors so we can analyze them. So here's my first segment, second segment, third, and even though the next segment may look like a continuation of the same segment to you, I'm going to mark it as a fourth segment, and we'll see that something very interesting happens between those two segments. And then I got the fifth, and finally the sixth and last segment of motion here. So as we discussed before, I can't look at this graph and visually identify what's happening to the object. I have to interpret the graphs. So let's do this for one segment at a time. So the very first segment, my velocities are always positive. So I got positive velocity, and my acceleration, which is the slope of the velocity time graph, is positive. This one is sloping up as it moves to the right. So positive acceleration. And you'll recall that when velocity and acceleration have the same sign, my speed is going up. And that's consistent with the fact that this graph is moving away from the x-axis where you got zero velocity. So that also tells us that this object is speeding up in this first segment of motion. In the second segment, my velocity is still positive, but what about my acceleration? Well, my acceleration is zero. This is a flat line, so the slope is zero and the acceleration is zero, which simply tells us that the speed, and in fact velocity, is constant in this segment, so we have uniform motion here. In the third segment, I've got positive velocity. I'm still staying above the x-axis, but I've got negative acceleration. My slope is now negative, which tells me that the speed must be going down. This object is slowing down, which is consistent with the fact that it's approaching the x-axis. Now in my fourth segment, the acceleration is still the same. It's not changing between the third and fourth segment, but my velocity is now becoming negative. So I've got negative velocity and negative acceleration, which means that the object is speeding up. Now there's a couple of things happening here that we need to pause and note. Firstly, with no change in the acceleration, how come the object goes from slowing down to speeding up? Secondly, what's happening at this intermediate point where it goes from slowing down to speeding up? Well, we got one big clue here. Right at this point between these two segments, what is the velocity? Well, the velocity is zero. The line is on the x-axis. And the zero velocity simply means that the object is at rest. So right at this point, we've got the object at rest, but it's not sitting at rest for a period of time as we have seen in the past. It's only momentarily at rest. Another clue here is that before the object came to a rest, it was moving in the positive direction. Remember, positive velocity means motion in the positive direction. And then right after it came to a rest, it started moving in the negative direction because I've got negative velocity, which means I'm moving in the negative direction. So this is a turnaround point. The object slowed down, came to a stop, turned around, and started moving in the reverse direction. Can you think of an example that would be consistent with that? Well, it could be a ball that I tossed up. As the ball approaches its maximum height, it's moving in the positive direction going up, but slowing down, momentarily comes to a stop at the very top, and then starts to speed up as it falls down, moving in the downward direction. So this could represent that kind of a motion. It could be a pendulum that's swinging to one extreme and then stopping momentarily before it starts to swing back and speed up. So those are the kinds of situations that this graph here is depicting. And in both of those situations, the acceleration does not change, even though the object slows down, comes to a stop momentarily, and speeds up in the opposite direction. In the fifth segment, I'm back to uniform motion. I've got negative velocity and acceleration of 0, which is uniform motion. And in the last segment, I've got negative velocity, but positive acceleration. The slope now is positive. So this object's speed is going down. It's actually slowing down. Okay, we're now getting close to describing this entire motion, but a couple more points before we do that. First, let's talk about where the object was at rest. At the very beginning, we got 0 velocity, so the object was at rest when it began. And in the middle here, we've already discussed it came to a momentary stop. And at the very end, it slows down to a stop as well. The velocity again becomes 0. Next, for the first half of the motion that I'm showing here, the object was moving to the right. How do we know that? Well, it had positive velocity always. And this is where I'm filling in a little bit of gap in this question. And I'm assuming that this velocity positive means to the right and negative means to the left. I could make any other assumption, but I just need to stick with the assumption I make. So I'm just going to use this. And then for the second half, I'll use a different color to contrast. The object is moving to the left. Negative velocity means motion in the negative direction, which based on our assumed coordinate system means that the object is moving left. And if we look at it more closely, segment by segment, the object is starting from rest, speeding up, moving to the right. Once it reaches its objective speed, it goes on cruise control and maintains that speed for a period of time. And then it starts to slow down, coming to a stop momentarily, turning around, moving to the left, speeding up, going on cruise control, slowing down, back to a stop. So what might the motion diagram of this object look like? So I got the object here at time 0, and then it's speeding up. So it moves over here, here, and here. And then it's on cruise control. So at this position, it's going to move the same amount in a given time interval. And then it starts to slow down. So I go over here, 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 coming to a rest momentarily, but then speeding up again, going in the left direction. So it's going to kind of retrace this motion, but I'm just going to show it in a different color, going back and offset it down a little bit so you can see what's happening. So the object then starts to go like this. So for the first half, we got it speeding up, cruise control, slowing down to a stop momentarily, and then turning around, speeding up, going left, cruise control, slowing down, coming to a stop. Notice that the object comes back to its starting position at the end, so it simply went to and fro. So the total displacement in this case is simply 0. Remember, displacement only cares about the starting and ending point, so any motion where the starting and ending point are the same, the total displacement is 0. Can we see that from the graph here? Sure. Remember, displacement in a velocity time graph is the area between the x-axis and the graph. So here I've got, for the first half of this motion, I've got a positive displacement. That's this area. And then for the second half of the motion, I've got a negative displacement. That's this area. And given the symmetry in this problem, even though we didn't work with numbers, we can tell that the area above the curve and the area below the curve are equal. And when we add those two, the positive and negative will cancel each other, giving us 0 displacement. Okay, as a final step, I've shrunk and moved the motion diagram to the right over here. And let's take a look at the acceleration versus time graph for this and the position versus time graph and see if we can make sense out of those. Well, as we mentioned, acceleration is simply slope in the velocity time graph, and it's constant for each segment. For the first segment, it's positive, and a positive constant value will simply be a flat line above the x-axis. So again, since we don't have numbers, I don't have a specific number here, but it'll be a straight horizontal line above the x-axis. For the second segment, it's constant at 0 acceleration, so it sits on the x-axis like that. For the third segment, it's a negative acceleration that's the same amount of negative. This slope and this slope are equal even though they're opposite in signs. So it'll be the same distance below the x-axis as the first segment was above the x-axis. So like that. The next segment, it's still the same negative acceleration, so it'll continue to look like this. The next segment, we've got 0 acceleration again, so it'll sit right on the x-axis. And for the last segment, back to the positive acceleration we had at the very first segment. So that's my acceleration time graph for this motion. And finally, let's look at the position time graph. So for the very first segment, we can see that the velocity is always positive, number one, and it's increasing during the segment. So that tells us that on the position time graph, I've got to have a positive slope because slope on position time graph is the velocity. And I've got to have an increasing slope as the time segment marches on. So it's going to look something like this. It starts at a 0 slope, and it's a steadily increasing slope getting steeper and steeper as we go on. For the second segment, the slope remains constant. So I've got a straight line that looks something like this. For the third segment, my slope is always positive, velocity is always positive, but the velocity is approaching 0 at the very end. So I've got a positive velocity, meaning a positive slope, but a slope that's constantly slowing down to become flat at the very top. So it's going to look something like that. It flattens out to be 0. For the next segment, it starts up at a 0 slope, and then the entire slope always is negative. So it's always going to be going down as it moves to the right. And the slope has to get steeper and steeper because my velocity value, a negative velocity value, is increasing. So it's something like this. It starts off as a very flat curve and then has a much steeper slope at the end. The fifth segment, I've got a constant negative slope, so a straight line with a negative slope. And the last segment, I've got a negative slope that is approaching a flat line because I'm coming to a rest at the end. So there is my displacement time graph. And a couple of things to note here. I've got uniform motion where I have straight line here and here. I've got 0 velocity where things are flat. So right over here, here, and here. Those are my 3 points where the slope of a position time graph is flat. And so that corresponds to the object being at rest even if momentarily. And all of that matches our conclusions from the velocity time graph. I didn't say too much about the acceleration time graph. There's not too much interesting going on here, except just to note and remind ourselves that the acceleration time graph by itself does not tell us much. I can have 0 acceleration and the object is moving. I can have non-zero acceleration and the object is at rest. I can have positive acceleration with the object speeding up. I can have positive acceleration with the object slowing down. So the biggest takeaway from here is that the acceleration graph by itself does not give us much information about the motion. We got to put it in the context of what's the velocity as well. Okay, I admit that that was a lot, but hopefully you'll agree that this was a thorough review of all the concepts we've been talking about over the last couple of weeks. Thanks for watching.